applied cost data, as you can see, going back again 8 to 10 years, comparable numbers, and these are overall averages, and there's a wide range with each. The averages are pretty comparable at that time, $6 to $7 per ton for both materials, but it's worth noting that a ton of recycled concrete goes farther volumetrically than does a ton of virgin aggregate because of the lower specific gravity. You've got your natural aggregate particles that are included there, but you have a significant amount of clinging mortar onto the outside of those aggregate particles, which is a much lower specific gravity. So a ton of natural aggregate has, turn it around, a ton of recycled concrete aggregate has 5 to 20% more volume than a ton of natural aggregate. So we tend to do our placements and our uses on a volumetric basis, or our requirements are volumetrically based, I should say. So you can take those costs per ton, but then when you turn it into per usable volume, you're going to see an advantage here on the recycled concrete aggregate side. And single project savings, and this goes back to 2008 again, of $5 million or more have been reported. I believe that there have been some jobs that have been done since that time with even larger savings, but they're not out there in the literature that I've seen yet. Benefits of recycling concrete from an environmental sustainability standpoint: obviously we're conserving natural aggregates, we're conserving energy that's required for processing and mining, and a number of other resources. We're not using up landfill space. There's a reduction, an associated reduction in greenhouse gas emissions from the elimination of the activities you see here with the hauling and the mining and so forth. And there is a bit of, we kind of overlook this a lot of times. There is a reduction in the atmospheric carbon dioxide. There's a recapture, if you will, of atmospheric carbon dioxide by the exposed concrete there through a process called carbonation, where carbon dioxide is absorbed back into and is chemically combined with the calcium hydroxide to form basically more calcium carbonate in the aggregate itself, hardening the outside of the aggregate. So a lot of potential benefits, and again, as was mentioned previously, the actual benefits in any specific case need to be evaluated in the context of that particular project over its life cycle. So the first step in concrete recycling, of course, is to evaluate the source aggregate and the quality of that source aggregate and determine what uses it may or may not be appropriate for. Questions commonly arise with decracking, with ASR, whether they can be reused back into concrete. Most folks shy away from it. It has been done successfully. Most notable projects up in Minnesota on Trunk Highway 59 for the decracking was done about 30, 40 years ago, and that job still looks wonderful today. Alkali silica reactivity was recycled on a number of projects, but again on an interstate pavement, Interstate 80, out near Pine City, Nebraska, or Wyoming, is actually Wyoming, I guess, near the Nebraska border. And as long as appropriate steps are taken to downsize the aggregate size on the decracking, basically do what you can to keep the concrete dry, prevent it from becoming critically saturated. And on the ASR side, doing the typical things that we do to mitigate for ASR with the use of Class F fly ash or lithium or other types of treatments, granulated ground blast furnace slag, and perhaps blending to reduce the amount of recycled material that's used. In both cases, eliminating fines in particular. So there's more details on that in both the sustainability handbook there, as well as in the references that are provided that accompany that. Another interesting consideration is the fact that the production of crushed concrete will impact the quality of that material and the reclamation efficiency. And this is a simplified graph. This actually came from a German study. There was a similar one done here in the US back in the 80s as well that showed that when you use an impact crusher, for example, the horizontal or vertical impact crushers, they do a wonderful job of removing the mortar from the exterior of the aggregate particles. You have relatively low mortar content on the coarse aggregate fraction, but you have less coarse aggregate fraction to deal with. As you can see here, you wind up with more amounts passing smaller particle sizes, so you have less coarse aggregate being produced. And the coarse aggregate is the part that we typically see the greatest demand for, the most easy use of in base applications and back into concrete materials and so forth. So depending upon your goals and depending upon the material that you have there, sometimes minimizing mortar is a good thing. Again, for example, if you have a concern with the quality of the durability of that mortar, eliminating it's a good thing, but you have to recognize that you may only wind up with a 40% volume reclamation for coarse aggregate. You may have 60% fine aggregate to deal with, whereas if you are trying to maximize the reclamation and you have no concerns about the quality of the aggregate, the jaw crushers and things of that nature that don't produce quite as many fines may be the better option. I mentioned earlier about drained bases versus undrained bases. One of the concerns that we have with using concrete, crushed concrete in base courses when there is drainage, or even when we're stockpiling it prior to use in an undrained base or a concrete paving application, is what happens to that runoff from the stockpile. Because what happens is a byproduct of the hydration of cement is calcium hydroxide, and that's a very soluble material which is easily removed, and when it's dissolved it breaks down into calcium ions and hydroxide ions, and the hydroxide ions of course drive the pH up. And then that hydroxide ion may combine, as I mentioned earlier, atmospherically with the atmospheric carbon dioxide to form calcium carbonate, or what's sometimes called calcareous tufa. And that's the white stuff that you see coming out of the drainage pipe here. This again is near my house on Interstate 79. This stuff can create some substantial accumulations in the pipes, as you see here. Doesn't necessarily mean that the pipe's not working. As you can see, there's a lot of water flowing out of this pipe still, and the water's not up to the top of the pipe, so I'd say we haven't overcome the capacity of the pipe to still carry water, but it still is very distressing to see this material. Another concern that we have, skip ahead here, is people will see a vegetation kill, and you see here this was taken up in Minnesota when I lived up there several years ago. Again, a crushed concrete base material was draining, and as the effluent would come out the head wall for the drain pipe here, there was an area about 5 or 10 feet long where the tall grasses and stuff were at the very least damaged, if not killed. Okay. Typically you got beyond that, and between issues of neutralization with the rainfall that's happening in those areas, and you get a little bit of an acidic rain, along with just general dilution with the other waters that are flowing through the area, soil buffering, other sorts of things, you did never see this extend much beyond the region of the head wall outlet. And usually you didn't see it for very long after the pavement was placed, because after that calcium hydroxide is removed and dissolved off the surface of those particles, then there's nothing left to flow out, and you have a normal flow of material. So it's a relatively temporary effect, but it is still a real effect. Going back to the drainage issues for the clogging of the drain pipes, there are a number of approaches, and these have been outlined in an ACPA document, an engineering bulletin from ACPA on concrete recycling for pavements, and those are listed here. They include not only ways to reduce the amount of material coming from the aggregate, such as not using fine materials which have a higher surface area, and eliminating as much mortar as you can and blending with the aggregates, but also using high permittivity fabrics and things that are less subject to clogging, and wrapping the trench and not the pipe so that the water flows into the pipe and doesn't plug up on fabric that's placed around the pipe. Also the use of daylighted subbases. So there are a lot of different approaches there that can be considered. There are some direct considerations for concrete recycling on design and construction. The effects of the unbound recycled concrete on pavement design. It does have a secondary hydration process in which you will have what is initially an unbound material, but over a number of years it will become more stiff, and that additional stiffness may mean that you would have higher curling and warping stresses, so that might impact your panel length requirements. If you want to reduce those stresses, you would reduce the panel length. Might also impact the thickness, either to offset higher curling and warping stresses or to be reduced because you have a greater stiffness pavement there, greater stiffness foundation. Becomes almost a stabilized base. There are also impacts on mixture design for the concrete if you're putting it back into a concrete mix, and the effects of crushed concrete on hardened concrete properties and concrete pavement design inputs have been quantified for consideration as well. There is an AASHTO specification, MP 16-07, that discusses the use of crushed concrete in mixed design, and there's some research that's ongoing right now, some specifications and procedures that are being developed for the specific use of crushed concrete in concrete pavement design, because separate guidance on that is a little difficult to find currently. In general, the quality requirements and properties of the crushed concrete are the same as they would be with concrete being made with virgin material. The only real exception, the significant exception, is sulfate soundness tends to be a relatively unreliable test for crushed concrete. The numbers that you get do not indicate the potential freeze-thaw durability of that material. So that test is generally dismissed, and if you want to evaluate the freeze-thaw durability of a recycled concrete aggregate, there has been some work done now with the hydraulic fracture test in Indiana, and then just standard ASTM C666 or the equivalent AASHTO test can also be used. Materials related to stress, I talked about briefly already, that they have been successfully recycled with the appropriate steps taken for ASR and for decracking, and that whatever you do in these cases, it's important to make sure it works before you build a multi-mile test section in the field that fails prematurely. General guidelines for using RCA in concrete mixtures, obviously consider the fact that you have a higher volume there, which means your specific gravity is lower. Your absorption capacity tends to be a little higher, so your water demands are going to be higher. There may be a more rapid loss of workability in the fresh concrete. There's often a bit higher variability in the strength. To maintain workability, we may see some higher water contents, and of course if you don't want to increase the water-cement ratio, that means you're going to be using higher cementitious contents as well, which might mean higher shrinkage in that mix, and that needs to be considered in the behavior of the mix and in your design procedures as well. Other approaches, of course, the use of chemical and mineral admixtures, and making sure you get the right amount of air content. You'll typically see, if there's much reclaimed mortar used, you'll typically see higher indicated air contents because of the air in the mortar will be reflected in the air pod test as well. So trial mixtures are always a good idea. There's a general description in the text and also in the ACPA resource on the impact of using crushed concrete in new concrete mixtures, the impact on the plastic properties, the workability, the finishability, the bleeding, and air demand and air content, excuse me, water demand and air content. And they vary depending upon whether you're using just coarse crushed concrete, which is the usual approach, or they're using coarse along with some fine crushed concrete. And we are seeing a movement towards people using maybe between 15 and 30% fines as a replacement for natural fines in some of these mixes, because A, it's a place to use the material, and B, it actually seems to be somewhat beneficial in terms of the strengths that result. It kind of fills in a gradation that's often missing between our coarse aggregate productions and our fine aggregate productions, so it's of some use there. Design recommendations, and again, these reflect the consideration of this material as an engineered product, not as a straight-up replacement for natural aggregate. The fact that we may have to reduce our panel lengths a little bit, our slab thicknesses typically will not be any different, because even if we would expect to see perhaps a reduction in concrete strength with the use of a recycled aggregate, and we made no changes, typically there are changes being made in terms of reduced water cementitious ratios or other factors that will still bring us up to the desired strength. So strength and slab thickness usually aren't changed too much. Joint spacing might be reduced, as I mentioned previously, for both jointed plain and jointed reinforced. Load transfer is the same. Same criteria for dowel bars being used. Joint sealant reservoir designs, if you're a state that does do joint sealing, consider the fact that if there may be more shrinkage taking place because of the higher mortar content, there may be a little bit more movement at those joints. You may need to have a little wider joint sealant reservoir to accommodate that movement. Subbase design, again, same as conventional, except again considering the fact that you've got the need for a free draining subbase to keep the bottom of the pavement drier if you're using a moisture sensitive type of an application like decracked aggregates or ASR aggregates back into the concrete. Perhaps higher amounts of reinforcing if you're doing CRC or JRCP, and our shoulder types, no real difference there. properties of the hardened concrete when you're using it back into a mix. You can see those kind of summarized here. We can make adjustments in general to minimize these impacts, with the exception of things like drying shrinkage, and you're typically going to see a little higher number on the drying shrinkage side, and we're typically going to see a little lower specific gravity, and our permeability tends to be a little higher. So those things need to be considered in other aspects of the concrete pavement design. So approaches for improving the sustainability. You can see the general objectives: increasing the use of the recycled materials through testing and characterization, adjusting our production processes, and customizing the preparation of the source concrete. Those are all ways to help increase the use of the recycled materials. Got some slides a little later on that show a little bit of that. Reducing the life cycle emissions. Using RCA as an approach for sequestering carbon dioxide is the one thing that came up there, particularly with the finer aggregate materials as the fines are produced, spreading them out and allowing them to recapture some of the CO2 which is driven off during the cement production process, because that's basically what you're recovering there. And then reducing the use of virgin materials and transportation through on-site recycling. And again, all the benefits environmentally, economically, and societally are summarized on this table. So again, there's the four major headings here, and an example of additional testing. Besides the testing for decracking and testing for ASR and testing combinations of those materials for use in concrete mixtures, there are also some guidance that was developed by Attar Saeed and Mike Hammond here under an NCHRP study about 6 years ago or 7 years ago, I guess, for better use of RCA in Subbase applications. And they developed a table that provided guidelines with a series of test requirements using the micro-Duval test for abrasion resistance, basically, the tube suction test, and a number of stress tests, triax test, repeated load test, and stiffness test, resilient modulus. And the quality of material, the threshold values for these tests varied depending upon the traffic level that was going to be used on the pavement on top of it, the environmental conditions, the moisture conditions, and with those sorts of things in mind, and the general climate, whether it's a freezing climate or not, those sorts of things in mind, you could have relatively low quality materials that might not be suitable for a high volume, high type application, but this identified lower level applications where they might be used. So this all goes back to the concept of using materials into their highest possible application for the most effective recycling. This is a quick slide that looks at breaking and preparing the source concrete. We have done projects where the asphalt has not been removed first, and the asphalt and concrete are commingled, and it's not uncommon to see as much as 20 to 30% reclaimed asphalt mixed in with the concrete and then used particularly back into foundation applications. But again, it may be more beneficial to recycle the asphalt separately, as Hassan was talking about previously, the applications for that material, and then recycling the concrete separately into its highest application. We need to be careful about how we process the material for the application. Again, the hammering and breaking operations in the field and the handling can have an impact on how much fines are produced and how much material is available for use for production of a coarse aggregate material later on. This is the graph that illustrates the sequestering, the carbon sequestration by crushed concrete over a period of time. It does show how atmospheric carbon dioxide is removed on a pound per pound basis of the crushed concrete on an annual basis. So it is a significant effect, and one that we often overlook. And then there's the whole on-site versus off-site processing question. This is actually an on-site plant, although it looks just like an off-site plant. Obviously, if we do it on-site, we eliminate all the hauling that's associated, and we eliminate a lot of the societal impacts of having the haul trucks on the road and interfering with traffic and so forth. We can do it on-site. We reduce those things, and there's a pretty good potential for cost savings, some of which is going to be offset by the cost of hauling in and setting up a portable crusher plant. In-place recycling, if we're using this material back into a foundation layer, we can eliminate even the hauling and crushing costs that are done with on-site processing here by simply using a mobile crushing plant and windrowing the